for inviting me to talk to you guys for today. Yes, as I've said, I'm talking about EMIC waves, or electromagnetic ion cyclotron waves, in the MMS era. Try to pack as many acronyms as I can in that one title. So very quickly, oh, excuse me, sorry, there we go. So quickly, I just would like to thank my research collaborators and the contributors who've been helping a lot with all of these studies, some of which I'll be talking about today, as well as the folks who are on the MMS mission and have really done phenomenal work in getting us some really awesome data for so many years. With asterisk beside them as high school interns I've had working with me on some of these projects the past few months. So they've been really a lot of fun. And I'm really glad that I've been able to have them on board with me. All right, so just wanted to start with a very brief introduction to EMIC waves. So electromagnetic ion cyclotron waves are essentially instabilities driven by ion temperature and isotropy, where we're talking about the perpendicular temperature of these distributions being much greater than the parallel temperature. And so we know why we care about these waves is that they're quite important for several processes throughout the magnetosphere, as well as in other regions of space, like in the magnetosheath, where you can have these resonance with particles that cause especially energetic particle loss through pitch angle scattering. As ion durability, ion temperature and then circling by my mouse is a pretty familiar relationship that related over parallel -1, the plasma beta. So basically the plasma pressure NKT over the magnetic field pressure, B squared over 2 mu naught. And so S and A alpha parameters that were derived using linear theory set to a particular value of wave growth. And we've been using a kind of parameter of the relation in conditions, which is the free energy from that temperature and isotropy, and other background plasma conditions that can act as a catalyst, essentially. To the, so essentially act as a catalyst for setting or allowing these waves to occur. Okay. So I'm going to turn my video off real quick just to help with bandwidth issues in case that's, to help with not cutting in and out. So excuse me, one moment. Today is not the day that I needed it to, Comcast to not be good. Okay, so continuing on. What I'm showing in here basically is from some MMS observations of what these EMIC waves look like. And actually what's really nice with this particular event is that this is really lovely long train where we can see some of these different characteristics go plasma. So these should be transverse electromagnetic waves. So basically in the plane perpendicular to the magnetic field. And you see the emission in both the electric and magnetic field, and usually pretty narrow band structures, as we see here. They're left-handed circularly polarized. And so if you're looking down the field line, you should see them going in a clockwise direction. And then their wave vector K, which describes the phase velocity of these waves, should ideally be parallel to the background magnetic field. Now, for most conditions, that's where you'll have the maximum amount of wave growth. And so when we think about these waves, because they're driven by these ion temperature anisotropies, what you'll see is that they'll have wave frequencies that go up to asymptotically to the local jets that are present that can influence the wave generation. So kind of looking at this a little bit more schematically, what we mean by that is basically when you have a simple proton band EMIC wave in a simple plasma, background plasma conditions, what you can see is like along this alphanic branch, this left-hand mode that goes up and asymptotes right around the proton cyclotron frequency. Now, when you start you can actually have these accomplishments where basically you have asymptotal and this the wave is completely different. So moving on, history of EMIC wave research, because that in itself can take quite some time. So what I'm showing here is an old observation. Oh, okay, thank you. I'll make sure to slow down just a little bit. What you should be seeing is just is a figure from the AMPT mission, where basically we have from top to bottom some of the wave ellipticities and wave power as we go as AMPT went through its orbit. And so we see that this is actually from 1984. So we've been getting these really nice observations for decades. But really these kind of things rose, the early theory for the EMIC waves is particularly in collisionless plasmas in the magnetosphere, arose about in the 60s, where it's starting to delve into this kind of how we can actually control the ion temperature anisotropy through this instability. From there were some pretty seminal works in the 1980s where we had some of the first spacecraft observations out in the magnetosphere. And then that's where the theoretical understanding of these kinds of resonances and the effects of composition and those stop band features were really beginning to be on. There's some significant research on by AMPT observations and some increasing modeling capabilities in the 1990s. So there's a series of papers in the early mid-90s that moves forward from an early first on distribution functions that had of the resonant interactions. And that's where that parameterization of the relationship between the proton temperature anisotropy and plasma beta really came about. And so more recently, with some of the mission magnetosphere, like CRESS and Van Allen probes, and now RSA, we've really learned a lot about these EMIC wave interactions with the energetic particle population, specifically thinking about how they affect radiation belt populations, as well as the more complicated avenues of some of these non-linear wave growths, like falling and rising tone emissions.
Sarah,
as well as some other triggered emissions.
Sarah?
Yeah.
Sorry to interrupt you, but I think we have a terrible.
Can you hear me?
We have a terrible connection problem. I mean, even the slides, I think they're coming out.
I'm not sure.
And somehow, I mean, what slide do you think you're on? I mean, right now, I think I see slide 4. Is it where you're supposed to be?
Okay, so so that would have been what I just, oh, actually, give me 1 second, Chris. I'm gonna, you know what it is? I have one thing to try.
Are you on a VPN by chance?
It is getting off. Yes, I am. And I didn't even think about just getting off VPN will help.
Oh, yes, that can help.
Okay, cool.
Yes.
Awesome. Yeah.
Okay.
Yeah, that's been one of the fun things about working from home.
Okay. Sorry about that.
Yeah,
no problem.
It's already
Thank
better.
you for letting me know. Okay, so and actually, please feel free to stop me, whether that is actually for technical issues or for any kind of questions or anything. By all means, jump on in. So I just went through a very brief and abbreviated rundown of some of the past work we've done over the decades. And so coming on to this slide 5 now, what we had is that we've had a lot of attention given more recently to intermagnetospheric EMIC wave observations, because we've had some really great observations within these regions that we hadn't had before. But we have known for decades that these waves are also pretty prevalent throughout the day-side outer magnetosphere. Now, I bring up this particular figure because it's a pretty popular one where we have these different plasma populations, and we can see where we get magnetosonic noise, and then chorus and hiss, and then other things like ULF waves. And then we have the pretty well documented region in the dusk to post-noon sector where you've got EMIC waves and where that plasmasphere is overlapping with ring current populations. But thinking back, if we've looked at, going back to some of our other older missions and even more current missions, so starting from AMT in particular, we have actually a lot of knowledge of these outer magnetospheric waves. And that's what I'm showing is in that early survey of these of the wave distribution from AMT. And then these are later bolstered by surveys from the Themis mission. Excellent, I'm glad to hear that that's better. And so from Themis, I'm showing some plots from Min et al. 2012 of the survey that they did over several years of that mission. And then from Cluster, where we had about 10 years of cluster observations throughout the magnetosphere. And so really, with all of these different observations over time, really what this picture in the middle, this schematic should really look like is that, where what we see is not only this region of enhanced EMIC waves, because we still do see that often, but also this day-side swath, as well as some really interesting dawn EMIC waves. And more recently, that I'm not going to go into here, are some really intriguing observations of EMIC waves at very low L shells. So I think I just want us to keep that in mind, that as we think about where we see these waves occurring, that, to start re-expanding our picture of these waves in the magnetosphere. So how does MMS fit in? Because ultimately, I'm going to talk to you about the MMS mission, which is near and dear to my heart. So the primary science of magnetospheric multiscale mission is to explore the physics of magnetic reconnection. But the orbit, the constellation configuration, and the instrumentation actually make it really suitable for studying EMIC waves, especially out in the outer day-side magnetosphere. And so kind of just as a brief overview of the mission for those who aren't as familiar with it, MMS is comprised of 4 identical spacecraft that fly generally in a tetrahedron, especially when it's out at its furthest point out at apogee. And this tetrahedron is usually at really small inter-spacecraft separations. And this has been on the order of tens of kilometers. It was launched back in March of 2015, with the prime mission actually beginning of September 21st, 2015. And it's still going strong. And so we've had multiple mission phases. And so the end of this video is going to show basically how we've been sweeping around the day side through the tail, and then the apogee will raise so we can go into that second mission phase. And so this first phase at lower where the apogee was at 12 RE was really to capture the day side magnetos pause. Now this apogee raise that you're seeing in the video playing on the right-hand side was showing the apogee being raised to 25 RE so that we could better explore magnetotail reconnection sites. Recently, it's actually been raised again, so now we're at about 29 RE. So what this video doesn't show as well, though, which is important, particularly in context of EMIC wave observations in the outer magnetosphere, is that not only have we changed the apogee over time, as I'm showing in the plot on the left, what we've also done is, what's also been happening is that the latitude of the apogee has been changing over time. And so when we were in these first early day side passes at about 12 RE, we're actually reaching down to about 25 degrees magnetic latitude, usually in the southern hemisphere. And as we go on in the mission at this higher apogee orbit, we're actually going to be precessing to even higher latitudes. And so we can really start exploring some other parts of the magnetosphere. And so within the MMS, there's also certain instrumentation that's relevant for EMIC wave research. One of the important things that we haven't always had on these kinds of missions is 3D magnetic and 3D electric fields. And this is actually pretty key, because one of the important things that we want to look at to understand how EMIC waves are evolving and propagating is how that energy is moving along the field line, and that is through pointing vector. And so having full 3D electric fields, which we haven't normally had, is really key here. Another good thing that we do have is plasma composition and ion distributions at a pretty decent time cadence. And so some of the surveys, some of the large scale surveys and observations from previous studies have been limited in being able to delve into some of the composition associated with the EMIC wave events. And then really one of the really cool things that, it was first pioneered with some of the cluster observations, but has really been kind of pushed to its limits with MMS is the ability to use multi-point measurement techniques like those that involve timing analyses and those that involve gradients. And that's because of this tetrahedral configuration that we have, which lets you do things like the kilometer technique, which I'm showing the schematic of how you get to those vectors from Dunlop et al. 2002. But also one of the big things that's very helpful here is that we actually are at fairly small spacecraft separations. So when you're doing things like looking at coherence scales, what you can know is that for lower frequency waves like EMIC waves, your tetrahedron is going to be at a size that's conducive to be seeing the same wave without any issues of ambiguous timing, which we've seen in some previous studies with cluster. Okay, so what have we seen so far? So I'm going to step through just a few things, a few highlights from some studies that have come out so far from MMS. This is not exhaustive. There's more work out there and some details that I'm not going to go over. I also kind of want to mention that I'm really focusing on the observations, and there's actually a lot of really great modeling and theory work that has just taken off in the last few years. That I just, that's a whole other talk in and of itself. So what we've seen so far, I'm going to start here with a paper that came out a couple of years ago that was, going in the tradition of the statistical studies. And this was using the first year of MMS observations, the magnetosphere. And so they're basically looking at the wave properties like occurrence rate of the waves, polarization state. They broke it up into proton and helium band waves. Now, there wasn't quite enough data to really get good statistics there. And so what we've been doing is a different group, myself and a few others, in particular, Mark Ingebretson and his group, is actually been expanding our own list to incorporate observations from the start of the Prime mission in 2015 through the end of 2019. And so what you're seeing with the two panels, the panel in the middle and the panel on the right, is the distribution of these waves. So basically wherever we've identified a wave train, where that is in local time, and then rho and z GSE. So essentially you can see where that might be as far as latitude. And so what we're kind of seeing though, is you can already tell just from looking at the density of this distribution, is that the spatial distribution is pretty consistent with earlier surveys. So where you've got a lot of wave activity seen in this dust post-noon region, but also you're still seeing a lot out in this morning, in dawn region here too, and a little bit smattering out through the night side. And what you're seeing too is that this massive amount of observations over the years going towards higher L shells. And actually, it's also pretty consistent already with observations that extend up to higher latitude, like we've seen with cluster. So as we go forward, we'll be delving into these, not only just looking at some of the basic wave properties, but also delving into some of the associated plasma conditions and things like the pointing vector. So we can really get a feel for why we're seeing these waves when we're seeing them, and what that means as far as kind of global dynamics and how energy is being moved around in the outer magnetosphere. All right, so you can ask yourself, why are we seeing the waves in these particular regions, focusing on this outer magnetospheric EMIC wave observations? And so remembering that there's a pretty unique configuration in the outer dayside magnetosphere. So what I'm showing here is a simple simulation where you've got solar wind flowing in from the left, it's impinging upon the magnetosphere. And so what you can see is that because of this plasma coming in from the solar wind, when you actually look on the dayside outer magnetosphere, at the larger radial distances, you start departing from being a true dipolar field. And so I'm going to talk about compression in two ways. And when I talk about a compressed dipole here, it's this large scale compression of these L shells, basically because of solar wind plasma pressure imparting itself upon the magnetosphere. So the other thing we have actually are some pretty unique plasma populations that are different from the inner magnetosphere. And so this is just a simplified schematic of plasma convecting around from the plasma sheets, coming in just through general convection and also through substorm injections, and then basically coming in from the night side. And so because of this cross-tail electric fields, what you'll have is an energy dependent drift for the ions. Now, typically the ions, when they're higher energies, will come around and drift around to the dusk side, and a lot of those will become part of the ring current populations. But if they're not that high of energy, what they'll actually do is come around and still be primarily dominated by sunward convection. And so they're going to come around the dawn side and then drift around from dawn to noon. And then you also then do have, during really active times, the populations from the plasmasphere that suddenly find themselves on open drift paths and then pour out in this post-noon region as the plasmaspheric plume. And so one other thing to keep in mind too, so you have all these populations that are within the magnetosphere being moved around and being brought towards the magnetopause on the day side outer magnetosphere. And one kind of an obvious thing to keep in mind is that you do still have solar wind ions making their way in. And so either through reconnection or other kind of mechanisms like Kelvin-Helmholtz or through the cusps, you actually will get pretty regularly, we see this, where we have these, few to 10 keV alpha particles in particular for the low energies. And so some of these processes actually of that deal when we have this kind of compression and when we have enhanced convection or these particular ion drifts will actually lead to ions with higher levels of anisotropy in the outer magnetosphere, as well as this kind of different and variable plasma composition. And so I want to briefly then go into what some of these mechanisms are that lead to enhanced ion anisotropy in the outer magnetosphere. One of them that is from drift shell splitting. And I've got an illustration of this particular drift that's down below from Seibeck et al. In 1987, where basically if you have ions that are injected in from the night side, the ones that have higher pitch angles, so here the 90 degree versus the 30 degrees, will actually reach farther distances, radial distances as they convect towards the day side. And this is just a simple consequence of conservation of the adiabatic invariance. And so if you don't have a constant refilling of these particles, what that can lead to is basically a depletion of low pitch angle particles as you go to higher L shells towards the day side. And as the field line particles will find themselves on more circular paths, and so will stay more so at lower L shells. Another thing that you can have, and this is a result of that large scale compression because of the constant solar wind driving, is that at high L shells, the magnetic field minimum is not actually at the equator. What happens instead is that it bifurcates. And so you will actually find these two local minima in the magnetic field along that field line at higher latitudes, one in the north and one in the southern hemisphere. And what that can do is actually lead to some really interesting orbit trajectories and lead to these ions trapped in these off-equator regions. And these are known as Chabanski orbits. And what I'm showing here is from a study from McCullough et al. 2012, who was trying to understand the relative roles of drift shell splitting and these Chabanski orbits in generating these enhanced ion anisotropy in relation to EMIC waves. And so some of these orbits in particular, when they get trapped off equator, can actually keep further increasing the ion anisotropy. And so, yeah, these two processes together, because they can increase the ion anisotropy for large pitch angle particles and basically trap them at these local magnetic field minima off equator, it's been posited lead to EMIC wave generation regions that are away from the magnetic equator. And so I tell you this because we've actually had some suggestion of this from earlier observations, like from cluster, where we had, where the EMIC, where we have here in the lower left corner, this from the statistical survey from Allen 2015, this feature in the noon sector at these high latitudes where there's just a lot of wave emission. So from an earlier study from that group, they're actually looking at the Poynting flux of these waves to try to understand how these waves are propagating. And so whether or not, where in relation to the spacecraft, these EMIC waves may be coming from. And so the Poynting vector is actually a really nice tool for this kind of study because these waves will usually propagate either parallel, so up the magnetic field line, or down the magnetic field line, or anti-parallel, and that's dependent on the hemisphere that you're observing in. So what I'm showing here on the lower right panel is a simulation from Kim and Johnson 2016, where this is the Poynting vector, this is the field aligned component. And basically, if they launch a wave at the equator, it's going to emit, along, up and down the field line. And the wave modes that are going to dominate away from the source region are going to be the ones that are propagating parallel to the field. And so you'll see here that it's going up the field line, and you'll see below that wave source region, those waves are going towards high latitudes, but in the opposite hemisphere. However, as you can see in this particular simulation, you can hit these latitudes along the field line where the waves will pass through what are known as some critical frequencies. And at these particular locations, what you can have are things like reflection of these waves. And you can have other effects too, like mode conversion. But what's shown up here is these waves being completely reflected. And so actually turn back out and down the magnetic field. And so what that can do is actually, so when they were first observing the Poynting vector in relation to these cluster observations, and they saw this, back and forth of positive and negative Poynting vector, it wasn't clear if that was from a source region or if it was from these kinds of reflections at these critical frequencies. But actually recently, with some MMS observations, we had an orbit where we ended up passing through an hours-long wave train, and that's what I'm showing down here on the lower left, where you can see just for hours, we have these really beautiful EMIC wave observations. And so what we were able to do is actually use that Poynting vector information, and that's what's shown in this bottom panel here in the red and the blue, to actually show that this Poynting vector direction systematically changed over time from being positive going up the field to then that kind of back and forth bidirectional, and then to actually going down the field. And so with that information and associated ion observations, as well as some field line tracing, what we were able to show is that we actually did pass through a source region. And this was probably one of the first definitive observations of passing through an off-equator generation regions. And so from those observations, is particularly some of the plasma observations and the field line tracing, we were able to, to see that, yeah, this is probably primarily tied to these things like this increased anisotropy from trapped populations off equator that you will get with with Chabanski orbits. Now, this is really interesting because it has some really interesting implications for understanding those wave properties when we see them at this high latitude. So thinking back to that cluster observation. And so as we kind of think back about wave propagation and how these things will evolve and what happens when they go to these higher latitudes where some of these they may pass through some of these critical frequencies, I think there's a little bit more that we kind of need to think about as far as what that means when you're actually generating them at these higher latitudes. And also what that then is going to mean when we're trying to understand our observations and understand the effects of packets going in different directions, and which can lead to superposition. So I think there's some really interesting work that this opens up as far as just propagation and evolution of these waves when we have these off-equator generation regions. Okay, So I want to jump back though to another way that that's really unique about the outer magnetosphere and how you can generate EMIC waves out here, and that is actually through direct influence of the solar wind. And so because the solar wind dynamic pressure is quite variable, this can really actually lead to localized compressional EMIC wave generation out near the magnetopause. And so it doesn't really take much. So this is a recent study by Liu et al. 2019, where they're actually able to track solar wind pressure fluctuations, and that's in this panel in black here, that can drive these local ion anisotropy enhancements. And that's what we're seeing. This panel, this third panel here is a pitch angle distribution from the HPCA instrument, look where you can kind of see how this trapped anisotropy, populations peaked near 90 degrees are being modulated. And this happens essentially also because of trying to conserve adiabatic invariance. So basically you've got you're bringing these particles in a localized fashion. It's convecting inwards to higher magnetic field strengths as you're being, compressed locally. And so that can impact the anisotropy conditions. And since these, as we've talked, talking about the plasma populations that make their way out to the day side are already pretty anisotropic anyway, this can be enough to trigger these EMIC waves in these localized regions. But importantly, what's interesting about this particular observation is that you see this quasi-periodic emission as well that's related to these periodic solar wind dynamic pressure fluctuations. Now, you can also have much more dramatic events, like when you have sudden impulses from coronal mass ejections that impact the magnetosphere. And this can trigger waves as well when you're out near the magnetopause. This is an observation from Ingebretson et al. 2018 that tracked such a thing. So starting out from near the magnetopause at MMS, they actually also saw them throughout the magnetosphere. Excuse me, one second. Excuse me. Throughout. Sorry about that. Okay. So I was trying to drink water and it was not successful. Excuse me. So, but basically what they were able to do is kind of track how this pressure pulse is basically ringing the magnetosphere and causing these localized EMIC wave emissions from out at the magnetopause with MMS towards where Van Allen probes was, and then even further in towards geosynchronous orbit where we had GOES. They also saw them too in ground stations as well. And so one of the cool things here is, is that along with these kinds of these smaller scale compressions, so these are the kind of compressions that lead to basically a ringing of the magnetosphere. And so you can actually also set off other types of ultra low frequency waves and get field line resonances. And these can also be enough to actually oscillate the magnetic field enough, and can lead to modulation of these EMIC waves. And so that's actually, so in the Liu et al. 2019 paper, that's what they argue for causing these quasi-periodic emissions. And so you can see how these different wave modes and plasma populations are feeding back on each other to cause this really interesting emission. Okay, so I'm going to leave kind of the regions and these more macro drivers of EMIC waves, and I'm going to go down into what MMS is actually really good for, which is looking at some more microphysics of the processes. So not just reconnection, but here we can actually start exploring some of these wave particle interactions. So I just want to highlight a paper that came out a couple years ago, Kitamura et al. 2017, where they were able to delve into the ion distribution functions and the wave observations in a really interesting way. And so kind of what you're seeing here at the top is this EMIC wave that they observed. And below that is there are some local helium plus populations. And so then we have a pitch angle distribution of total ions in a particular energy band, where you can kind of see where we have enhanced 90-degree pitch angles right when we start seeing this wave. Now, what's really kind of cool is then being able to actually look at that in gyro phase, as well as in phase angle. And that's what the next two plots show. And then finally, the last one is really looking at how the energy is being dumped from the fields to the plasma. And so you can see that there is a transfer of energy occurring right where we see this most intense peak in our helium and in our ion populations here. And right where we see this kind of localization of the population in this phase angle space. And so with that, what they concluded was that this was a direct transfer of energy between this EMIC wave and these local ion populations that they were able to capture in a really kind of clear fashion. And I always love a good cartoon, and I think this is a good cartoon. And so basically where we have this wave, and that's in blue traveling on the field line, and first it's actually interacting with protons in a resonant fashion, but then that also leads to these non-resonant interactions with the helium that's around. And so what part of that involves getting that phase bunched population that we see. And that actually, that kind of non-resonant interaction was actually discussed early on by Mach 1982, and this should lead to energization of these helium ions. And as we see that it does, we actually do see this intensity increase in this particular event. But this had never really been clearly observed before. And so as we go through the MMS observations, I think we'll have opportunities to really dive deeply into the ion distributions and to see how these waves are resonantly and non-resonantly interacting with the local plasma. So I want to highlight just a couple more things. And really, so I know I went micro real quick, but I'm also going to come back up and talk about the EMIC wave vector. So part of this is when we want to really understand wave propagation and resonance conditions, a lot of it comes down to, do we understand the EMIC wave vector? Because those particular things are very sensitive to the EMIC, to this vector. And so as an example, when we have K and we have a K, that direction that changes relative to the background magnetic field, it can change these conditions. What I'm showing here in these two panels is a simulation of an EMIC wave, where in the panel on the right hand side, the wave is being set off with the idealized wave vector, which is going to be parallel to the magnetic field. So the angle between the two, the K and B, is 0. And you can see how it propagates up. It goes to high latitudes, has this interaction to these critical frequencies, and goes, is reflected back to the higher L shells. But when you have EMIC waves that are generated and that develop, or that are generated and propagate with an oblique normal angle, so in this case, they used 40 degrees here, what you start seeing is actually this can have kind of pretty big effects on what happens to these waves as they move along the magnetic field. And so in this instance, not only do you have some of that reflection, but you also have some unguided propagation where these waves will then be later seen in regions that you wouldn't necessarily expect them. And so the wave vector also can affect things like the trapping and gyrophase bunching as well. And so that has pretty important implications for looking at EMIC waves in the inner magnetosphere, where it's really the diffusion coefficients that lead to interactions with energetic electrons in particular are really sensitive to this wave vector. Interestingly, plasma composition can also play a role in determining some of the properties of K. So this is so from the same authors, they also had a simulation where they were changing the background composition, so including some helium plus ions. And so immediately what you can see is that you do start getting from this pretty idealized wave that's propagating just along the field to these more intricate and more complicated features. And so one of the things that we've had issues with for decades is that the full knowledge of this vector is pretty difficult to obtain observationally. we've had multiple kinds of single spacecraft methods and we can get some information, but the full direction and the full magnitude of this vector is pretty difficult to get right. And so what we can do now and what we've been increasingly doing as studies with current and ongoing studies is actually utilizing multi-point techniques to determine this really important quantity. Okay, so I'm just going to go highlight two particular things that we've been using more readily. And I would also like to say that even for some of these single spacecraft techniques, like those that use singular value decomposition, you can actually do that to a really nice degree. And that's because we have really great calibration on our magnetic fields. And then we also have those really nice 3D electric fields to use when you go to do that matrix inversion. So there's a lot of really cool things that we've been diving into. And so some of the studies that I've been talking about and that have been ongoing use phase differencing to pull out the wave vector. And I'm showing an example from Liu et al. 2017. And so the plots on the bottom right is just an example where we have the 4 spacecraft all seeing the same wave and nearly identically because they're pretty close separate interspacecraft separations. And with that, what you can do is actually between these different spacecraft pairs determine the best fit to a time lag between these observations. So you're basically doing a timing analysis. So you can actually pull out this difference in the timing here and invert that to get the wave vector. And so that's kind of what I'm showing here. So you have the 4 different pairs of spacecraft and then comparing each of these. And so basically you have 6 different combinations and so what you can do is actually then also look at the error in your methods by evaluating all of the available pairs to understand just how well you're getting this information. Another thing that we've been doing lately is actually developing an implementation of a technique that we've dubbed our wave curl analysis that uses the curlometer to pull out the current density that's associated with the wave. And that's kind of what I'm showing. And so in the figure on the right-hand side, in the bottom panel here, where my mouse is, and in the third from the bottom panel, that is the wave associated current density using curlometer. And basically what we do with that and with the wave magnetic field, which is here in this 4th from the top panel and second from the bottom panel, is basically put that in Fourier space and use Ampere's law to pull out K. And so this lets us basically kind of directly solve for this vector. And so an example of that, looking at the highlighted region on this right-hand side plot, when you actually pull it through in the Fourier space of that wave, what you can actually do that cross product directly. And then what we've done here is actually evaluated that not only with this technique, but also with phase differencing and another method that uses Ampere's law from Bellin 2012 and 2016 to evaluate kind of the robustness and the accuracy of this particular method as we compared to the theoretical solution that we get, which is shown in the contours here and the colors on the bottom. That is the wave growth from the dispersion surface that we get using WAMP. And so kind of what we can see here is that these methods are actually pretty good as far as getting when we're able to compare it to the theoretical dispersion relation, especially when we have a really nice clean observation. And for this particular instance, we also happen to have a really fortunate opportunity to have a full plasma distribution. We were able to actually see nearly the entire distribution because of the energies that we were looking at. And so really what this does is that it actually gives us the full information that we need. So not only do we have the direction, and so can understand the wave normal angle and how that's evolving, we also do have the magnitude of K. So we can actually get out the wavelength as well. And so what we're going to be doing with this is actually looking at these wave vectors on a large scale to understand how and why we're seeing what we see and how that is related to the background plasma conditions, distance from, possible source regions, and then delving into effects like when we have these multiple wave packets and superposition. So there's a lot to be done in just really understanding some basic properties of these waves that with these multi-point methods and advances in our plasma instrumentation and composition observations and our theoretical understanding and wave modeling, we can really start to answer some questions that have been left open by all of the previous observations and theoretical work that's been done. And so I kind of just want to now do a recap in a quick rundown of the recent studies that have come out of EMIC waves with MMS. So you can see some of the main themes that are emerging over the past couple of years. And so first, one of the really cool things is that we have a really comprehensive view of the outer magnetosphere. And so, we started with that 1 year of observation, but now we have years of these wave observations and composition with multiple passes throughout the day-side outer magnetosphere. So we can really begin to understand on a statistical level what we're seeing and why. One of the really cool things and why I think that, this is an era of MMS is that we actually have an unprecedented number of spacecraft also in different regions of the magnetosphere that can be used to have in combination with ground-based observations for a really complete view of the occurrence and extent of these waves in magnetic local time and L shell. So I think, and so kind of like the example I was showing from Ingebretson et al. 2018, we can track if for some things, we can kind of track these waves as they're moving through the magnetosphere and the extent over which we're seeing them. So one big thing here, and I didn't touch on it quite as much, but there's some really nice examples of work that's recently come out and under review, is that the composition here is really important. We have known that for decades, but I think now we're actually at a point where we can really dive into that and start testing out some of those theories and start really understanding, the role composition plays in driving these waves and in particular, producing some of the wave properties that we've seen that have puzzled us in the past. So that's some of the studies coming out by Lee et al. 2019 and 2020. One quick thing I didn't talk about here, but it's really, really neat, is that we've actually seen the presence of the He2+ band inside the magnetosphere. This was only ever seen out in the magnetopause boundary layers and magnetosheath, where you expect to see it because that helium-2+ is the predominant heavy ion in that, out in the sheath. But we've actually have increasingly and pretty consistently seen those kinds of, stop band features as we get to really large L shells in the magnetopause. Another thing that I didn't talk about, but it's a really interesting paper, so I highly recommend going to look at it if you're interested, is understanding how we can use these observations to better understand oxygen cyclotron harmonic emissions and the associated ion distributions. Now, Usanova et al. 2019 was looking in the plasma sheet boundary layer, but we've seen these really intriguing EMIC wave, or maybe not EMIC wave emissions. I think actually we don't really know for sure, at really low L shell as well. And these are thought to be caused by ring distributions from oxygen populations. They're not really well understood, so I think there's a lot we can do there to really to advance our knowledge of these other mechanisms for generating these waves. So, and I did talk about this, I won't spend long on it, but what we're really seeing here is that is the importance of these different mechanisms that are leading to EMIC waves, from localized compressional events at the day side to increased anisotropy from Chabanski orbits and drift shell splitting, and the things that are leading to these off-equator generation regions, and how we might further understand those and the implications for wave propagation as we go on. A cool thing, and I only briefly mentioned the first part of this, is basically diving into the cross-species and cross-frequency coupling and modulation. So as mentioned earlier, when we out in the outer magnetosphere, those kinds of localized compressional events can lead to ULF waves, which can actually modulate that EMIC wave emission locally. One of the things, though, that USNOVA et al. 2019 was also looking at was how chorus waves may be also contributing to modulation of the emission that they were looking at. And that's kind of a new area that I think I for one, am not as familiar with, but it does sound quite intriguing to understand how these different wave modes are interacting, because the magnetosphere is a very complicated place. And so really now too, we can really dissect some of these wave particle interactions, and in particular, some of the ion distributions. So looking at both resonant and non-resonant interactions with the local, heavy ions in order to understand energy transfer, but also looking further at minimum resonant energies for when we have parallel and more oblique wave vectors, which can determine the extent of energetic electron scattering. I would say that there are some really odd features in early AMT observations of ion distributions that we haven't really revisited. And so I think it's prime time to look back at those distributions. And that's actually, one thing that is on my to-do list for some of the studies the group that I've been working with are doing right now. And then really, finally, the thing I want to point out here is that we're taking a full advantage of these multi-point measurement techniques to discern these key wave properties. And I think that's where we can really move some things forwards by utilizing these, techniques like phase differencing and the technique that we've been developing, utilizing the wave-associated current density. We can actually explore these wave vectors. And as well, we can also really deeply look into phase and period coherency between the spacecraft, because we actually are close enough together that we know that we're looking at the same wave when we have these individual waveforms. And so I just want to leave you with quick notes of, going forward as the MMS continues on. And so we've had the capabilities to really explore the dynamics in the outer magnetosphere, like the EMIC waves that I've been talking about for a bit, and other plasma instabilities, but also with things like plasma composition and the effects on processes that are occurring on the day side, as we've been seeing, including wave particle interactions. For the study of EMIC waves, we have this nice opportunity to really address these questions that were left open by AMT and CRESS and cluster and Themis and even the Van Allen probes. And that we can so really not only understand what we're seeing in the outer magnetosphere, but in understanding fundamentally how these waves are being driven and how they are evolving, which can have some implications for where we see these waves anywhere. And so along with detailed investigations of individual EMIC wave events, the years of MMS observations we've been accumulating in these regions, and particularly the outer day magnetosphere, enable us to explore on a large scale some of these fundamental aspects of these waves, and in particular the wave vectors and the propagation of these waves as the plasma and magnetic field conditions vary in response to the upstream solar wind driving and changes in magnetospheric convection. And so with that, I just want to say thank you for your time, and I would be happy to take any questions.
Great, thanks so much, Sarah.